Hello and welcome everyone as everyone joins. We'll just give it a few seconds to allow people to get up to speed. Make sure you can hear us and see the screen. Great to see so many people joining again today. Already at nearly 40, 45, 50 attendees. Fantastic. We're hoping we had almost a record number of sign-ups actually for this event. So really excited to be here for the next hour. We're at 70, 75 attendees, 80. That's brilliant. So welcome to the latest online seminar from InstallerFest. Today we have Christian here joining us from Viessmann, which is for those who don't know, a German manufacturer of all heating and industrial systems. Germany has engineers where the UK has installers, and Christian's an engineer here to talk us through a non-brand specific introduction to heat pump technology. And this is hopefully tailored for everyone. So kind of a complete introduction for gas and heating installers. And just before I formally introduce Christian and we get started, we have a quick poll just to see why you guys are joining today, and what is the primary reason for attending this event. Is it something where you are just trying to keep aware of the latest trends in the market and you're about learning, or is this really about growing this area of the business for you? Do you see this as a huge opportunity to grow your business? And then following up to that, do you see yourself as becoming MCS registered for heat pumps directly, or perhaps through another company's MCS umbrella scheme? So great, we've had just over half the votes coming through. It's really interesting. We've got, I think, quite a lot of people looking at the professional learning opportunities, which obviously this whole festival is really about, but also a good portion looking to grow their business. So that's 85% of people have voted. That's probably enough. Hopefully that came up on your screen. Do send us a message if you've got any trouble accessing it. And also, just please do fire in your questions. You can either use the chat function where everyone can see it, or if you prefer to ask anonymously, you can use the Q&A feature as well. And we will try and feed those questions. I will ask some back to Christian. We also have Darren on the line from Viessmann as well today. And hopefully we'll answer as many of your questions as possible as we go. Any others we'll try and pick up at the end, or we'll follow up with you directly after this call. So thanks for joining, and let me just end that poll and share those results with you now. We've seen significant amounts of people looking at the learning opportunities, so hopefully Christian's introduction will provide that, and 45% planning to get MCS registered as well. So great. Christian, what's your sort of reaction to that, and would you like to give a quick introduction to yourself?
Yeah, good morning. It's Christian Engelke here from Viessmann. Yeah, looking at the initial poll results, that looks very good. So yeah, hopefully there is something in here for everybody. I'm trying to cover, sort of the introduction of air source heat pumps, but obviously from the manufacturers like Viessmann's point of view, there are obviously some key technical areas, aspects of the design and the operation of the heat pump, which are very important. Also the aspect from becoming an MCS registered installer. Obviously we do know that MCS has got an important part to play, certainly when it comes to installation of heat pumps, certainly for customers who want to benefit from the RHI incentives. So that's good news. Yeah. Good.
Great.
So
great.
shall we start?
Give us a quick introduction? Yeah, absolutely.
Good. So yeah, good. Let's start. Good morning all again. So to our webinar regarding the introduction of air source heat pumps. This morning I will just cover a few aspects here. So we have the heat pump market, just outlining the installation and the market of heat pump products today, and what the expectation is in the next few years. Also we are talking about the technology itself. What is a heat pump? I'm introducing a few key components of a heat pump to give you an idea of how important they are and what they're doing. Heat pump efficiency is one of the key messages we want to, as a manufacturer, want to get across. It's important to understand the efficiency, where it's coming from, what it does, but also how heat pumps are being sized in applications. So this is something which we get to hear a lot from people, because obviously there's lots of noises being made from the government and industrial bodies about how important the heat pump sizing is. Noise emissions, again, another aspect there, because obviously the product is located mostly outside, so there are noise emissions to be considered. I will just go through some very basic, typical hydraulic schematics, and then, and finally a quick update on the Viessmann range of air source heat pumps. So, starting off, the heat pump market in the UK. Heat pump market in the UK has been, from the heat generators point of view, has been the largest in Europe. We know that gas boilers are being about 1.6 million installations every year, and is the dominant heat generator in the UK from the installations point of view. The other, which is the dark grey shaded area, representing the wall-hung boiler market. The heat pump market in the UK has been, for the last 10 years, has been relatively stable, growing maybe the last 12, 15 months because of the noises coming from the government. But we're talking about a relatively moderate market of 25,000 heat pumps so far. Large proportion of these are air source heat pumps. Where is the market going? So you can find various resources and expectations of the market where we're going to be. Nevertheless, there is a great aspirations also from the government to grow the heat pump market. It's a very important product for the future of providing heating and hot water in the UK. And here is just one snapshot from a research company expecting the market to double in the next 5 years. There are other researches and expectations that maybe the market will grow even faster. But nevertheless, we do see a significant growth in the heat pump market, certainly the air source heat pump market.
And Christian, could I just ask you on that? Like, where do you see, what is driving that growth? Where do you see that?
Yeah, the main growth drivers are the new build market. This is from the government point of view, the low-hanging fruit market that can dictate the market by changing the building regulations and basically sort of making it less interesting for any planners and architects to specify fossil fuel technologies. Okay. Another big growth area we see is London, Manchester, Birmingham, where these cities have got their own local regulations. And again, fossil fuel boilers are becoming disadvantaged because of NOx requirements and also the disadvantage of being a green technology. The retrofit market is, from the government's point of view, the most difficult market. The off-gas markets, and we heard already news that the government is planning to maybe ban oil-fired boilers in the next few years. But the retrofit markets, the gas boiler market and the oil market are very difficult from the government. This is the largest market with more than 20 million households on gas to convert them. And that's the reason why the government is offering an RHI incentive scheme for homeowners to jump onto a new technology. So, this is I wouldn't say a focus market, but this is the most difficult market, and we were talking about most of the challenges in this market in the next few minutes. But there's an expectation that the market will grow significantly in the next few years, and there will be a big share of everybody to jump onto this. Again, just a quick update. Air source heat pump market is the largest proportion, most interesting. It is an interesting technology. It's easier to install, and also from the price point of view, homeowners are spending less money, less capital on the installation of air source heat pumps. And that trend will continue, and we do also see a trend now on the commercial side of it, that people are looking in large commercial installation into air source as well. So what makes heat pumps so attractive in the future, certainly new build market? This is a chart which has been around for a few years now. This gives you a trend of the building stock, the existing building stock, what the energy requirements are, and then with improving the building stock, the fabric, the insulation, windows, etc., you can see that the red blocks is the heat demand of properties is becoming smaller and smaller. And you can see that the hot water demand will continue to stay. It's more or less the same. People still use showers, baths, hot water, etc. So proportionally, hot water demand will become a more important role in the total heat demand area than it has now.
So the dark blue is hot water demand, and then
the dark blue is hot water demand, red is heating demand, and the light blue is the ventilation losses. So this is the defines the leakages of the property. And you can see that that is also proportionally now. We see that already with new build, that 30–40% of all heat losses is ventilation losses. And if that needs to be tackled, then new build properties needs to be fitted with heat recovery systems. Otherwise, the ventilation losses will still be proportionally much higher. So that's sort of the trend on the new build market. So of course, with the limitation on air source heat pumps on power supply in the UK, you know, residential homes are provided with 230 volts power supply to every home. You're limited with the heat demand, and with the ever improving housing profile and the fabric, the heat demand of homes will drop significant, and we see that already. So heat pumps are becoming very attractive for this type of applications. The renewable heat incentive is obviously, as I said, it's for the what we call the able to pay customers. So they can jump onto this the funding scheme which is available. The product and the installer need to be accredited under the microgeneration certification scheme, MCS. And you can see the attraction of homeowners that with air source heat pumps, they're earning 10 pence, 11 pence per kilowatt hour of heat generated, and that is over a 7-year period. So in money terms, homeowners can earn between £1,000–1,500 on the RHI incentive. These payments are deemed incentive payments, so they don't need to be metered, and that £1,500, £1,200 a year will then last for 7 years, and then it stops there. So this is a nice chunk of money for homeowners, where they can fund the extra bit of capital for having a heat pump installed. The RHI incentive scheme is been extended until 2022, so people can enjoy it, and beyond 22. The government is already talking about the replacement of the RHI. They're looking for a initial capital incentives for homeowners instead of having 3 quarterly payments paid to the homeowner. But this is still a couple of years away, so let's make use of the existing incentive scheme available so far. So what is a heat pump? Heat pump technology is more like a I would call it maybe like a bicycle pump. We pumping up a refrigerant vapor gas until we get a meaningful temperature. The way the refrigerant gas is being heated up, we're using large amount of we're calling it low grade energy. This energy can be from the ground, can be from air, or from flowing rivers, and then the heat pump is with the compressor is generating a higher temperature energy, which is then usable for space heating and hot water. The attraction of heat pumps is that we're using the ambient air freely. It's inexhaustible, it's available, it will never run out. And the other attraction from the government is that the bit of electricity a heat pump is using now these days are also very low carbon right now. So the electricity generation in the UK has been is using more and more wind farms and PV panels. So therefore the electricity generation is also becoming greener. And in the next few years, it's expected that the electricity will be greener than perhaps gas as well. So coupled with the high efficiency and the running cost, the heat pump will be the ultimate choice. And that's the reason why the government is so keen about this, because it ticks all the boxes for them to provide a low carbon technology.
It sounds amazing, really clever technology, Christian. Could you try and explain it to me as a layman and a lot of the people listening who will be explaining it to customers? You know, like how would you try and could you sort of sum it up in a sentence or two? Like how does it kind of work? It's basically taking heat from, I don't know, the air or that's already generated and converting that.
Yeah, no. So the explanation is coming a bit later, but we're using the fan. The air, the outside air is basically heating up the refrigerant gas, which is in a closed loop of the heat pump. It absorbs that low temperature air, so it doesn't matter whether it's minus 10 or 20 degree. It's still able to absorb that energy, and the compressor within the heat pump acts like a bicycle pump. Air pump, so it compresses that vapor and brings that low temperature point to a higher temperature point. So from 0 degree, let's say, all the way up to 60 degree. So that's what the compressor is for. The compressor is electricity powered, and that's where we are getting the efficiency out of this. But I will explain that later on. So it's all in here. Quick summary also that there are other heat pump technologies around. So we have, we're not talking about those today, but obviously ground source heat pumps have been around for many, many years, since the 70s. We differentiating three main different ground source heat pump technologies. So one is the ground collector. So this is where you're digging up your own garden and putting plastic coils into the ground about 1 meter deep. And you need a big area for this to extract the heat from the ground. Another popular solution, which is more space saving, is the borehole scenario. So you're drilling down to 100 meter, 150 meter into the ground, and then you're extracting the energy there. This is this technology is quite good because it's got consistent source temperatures, so it's about 10 degree consistently throughout the year, while the collector, for example, is more sensitive to the seasonal temperature effects. So, and then thirdly, we have the water-to-water heat pump source. So we're using flowing water mediums like flowing rivers or lakes, tapping into that and extracting the energy from that. So this technology, again, are quite useful because they are operating on a higher source temperature, so up to 10 degree or 15 degrees sometimes. So you're getting very high efficiencies out of those technologies. But for now, we are just talking about air source heat pumps. So this is here our most common technology, an outdoor unit there, extracting the air from the outside, and then there's pipes connected into the building and passing the energy into the heating system and hot water like a normal gas boiler. And another air source model is more popular in Europe. This model is actually fitted inside the building, mostly in the basement or in the garage, and there's ducting to the outside to draw the air into the building. The advantage of this one here is, of course, that you don't have the aesthetics problems having the outside unit located outside. Also in the build-up area, you don't have the problems with noise levels, so everything is contained within the building. But these are the two main areas there. This is from the UK point of view, the most popular choice. I would say 99.8% of all installations are this type of technology. So how does the heat pump actually work? So I've just given you a typical picture of an outdoor unit. This is here. You can see all the main components in here. You can pick up any manufacturer. They're more or less the same. So we have the gray shaded area here at the back is our what we call the heat exchanger evaporator. Then we have a big fan in here. The fan is drawing the air from the back of the machine through the evaporator heat exchanger. And you need to consider this like a car radiator you have there as well. So it's a thin tubes putting it through, and then you get cold air to the front. Here in this part here, this is where the compressor slits in. It compresses the refrigerant gas. You see all these copper pipes in here and the valves and expansion valves and so on. Moving the, pumping the medium around. And then once the medium is hot, it goes into what we call a condenser, which is a standard plate heat exchanger, and then transfers the higher temperature to the heating system or water. There are models there with an integrated circulating pump to pump it into the heating system of your property. Some models have it inside the building. So, but that's generally the general buildup of any outside unit. And you can now imagine that how difficult it is for manufacturers to make this unit very small, but also very effective. Because the biggest component in this outdoor unit is the evaporator heat exchanger. And you can imagine if you make that heat exchanger small and compact, then you need a bigger fan because the pressure drop of the expansion of the evaporator heat exchanger makes it difficult for a slow moving fan to pull the air through. So you need a bigger fan, faster fan speed, etc., to get the same energy through the smaller, compactor evaporator heat exchanger, and then you're creating noise levels. So although you may be making the outdoor unit fairly small and compact, you're creating other problems, which is the noise levels. Other issues with the evaporator, I'll come to that later, but it's water is building up on the fins. The fins need to be run off, or the water has to run off the fins effectively. Otherwise, you're getting an insulating layer on top of it, and then the efficiency will also then go downwards. So that's not very desirable. So that's a quick overview of an outdoor unit with the main components in there. Most manufacturers will provide this already prefabricated, factory fitted. So there's nothing you from the installation point have to consider. Another important part is the refrigerant gas. So this is the gas which absorbs the low temperature energy from the ground or from the air. The models are now, through European regulations, the refrigerant gas are now being disallowed, some of them now, particularly those type of refrigerant gases, because they are environmentally unfriendly. They're causing problems with the ozone layer, and they are expressed in GWP, which is a global warming potential. So you can see in red, these are very inefficient and they're very environmentally damaging. So manufacturers are being urged now, because the red ones are being discontinued. We have a couple of years grace to get rid of them and find the replacement. So you will find now new air source heat pumps with a new refrigerant, and you see it's green, it's more environmentally friendly, it's been approved. And that's the important part as well. With refrigerant gas, you need to consider also F-gas regulations. So if you do work on heat pumps, like with the gas ticket on gas boilers, you do need to be certified to work on heat pumps. With some heat pumps doing for the installation, like with monobloc units, where the circuit is already being pre-filled by the manufacturer, like in this model here, then of course you don't need to do it. But as soon as you are working on a heat pump, i.e. replacing it or refilling the refrigerant gas or whatever, doing some repair work, you do need a ticket for this to be F-gas registered. So the refrigerant gas, as I mentioned earlier on, has got some very important features. So we have the compression, hence the word of compressor. So we're compressing the refrigerant gas, and you know this effect from bicycle pumps. So the harder you pump, the warmer it gets. and that's the same with the compressor. So again, the heating effect is very important. And again, using just common sense you're experiencing with your bicycle pump, the higher then the pressure gets on your tire, the harder you have to pump. And this is the same as for the compressor. So the higher you're running the heat pump on temperature, then the compressor has to work very hard as well. And hence it uses more electricity, or efficiency goes down. Then we have the opposite effect within the heat pump, which is what we call expansion. So once the pressure is up and then the plate heat exchanger is taking the energy away, we need an expansion valve to get the pressure back down to a lower level. And then we know the expansion of any gases will also result in the cooling effect. And we need that, because then the cooled refrigerant gas is going back to the evaporator, and therefore the whole process starts again. So we have two important components in there. One is the compressor and one is the expansion valve. Good, and here is just a very quick schematic of the compression refrigerant cycle process. So we have these two heat exchanger I've explained. So one is what we call the evaporator heat exchanger, which is like a thin tube heat exchanger. Then we have inside that, we have the refrigerant medium. And when the ambient air is heating up the vapor, it starts to, or the refrigerant starts to vaporize. The vapor goes into the compressor. It will be compressed to a higher medium and higher pressure. And then it goes into the condenser plate heat exchanger and transfers the higher temperature heat to the space heating and hot water. And then the expansion valve is then bringing the higher pressure level of the refrigerant back down to the lower level, and then the whole process starts again. So you can see that the process is working very well in low temperature environments, and that's the reason why we're using certain types of refrigerant gases to make sure that the absorption of energy is optimized and very effective. So again, evaporator, condenser, and then the refrigerant cycle is moving all the way around with the compressor and the expansion valve as the main features, components to make it all happen.
And Christian, Patrick has a quick question, I think.
Yeah.
You said, do you only need the F-gas certificate when maintaining the refrigerant circuit, or is that for any component on the heat pump? Yeah,
no, only the refrigerant circuit. So there's products there like what we call split heat pumps. So that means you have the outdoor unit and then you're using refrigerant pipes to go inside the property where the indoor unit is fitted. Now, for those, you need also an F-gas ticket. But for normal installation of a monobloc unit where all this circuit, all these components are included in the outside unit, so it's a closed loop circuit. And that is pre-filled by the manufacturer and ready to go. So those products you can install without an F-gas ticket. That's a key advantage. And when you do some work on the machine, then only you need an F-gas ticket if you are doing any work in that refrigerant circuit. So if you work on the compressor, if you work on the expansion valve, there might be a leak on some copper pipes on the refrigerant circuit, you do need to work, you need to have an F-gas ticket. Any other components like circulating pumps or electronic boards, you don't need an F-gas ticket for this.
Okay, great.
Okay. So scroll compressor, and most heat pumps are using scroll compressor. That's also one which is Viessmann is using. It's been a very reliable compressor. The motions of the scroll compressor are demonstrated here in this quick animation. We have the refrigerant gases coming in on the outside, and then the scroll compressor is compressing it towards the center point of this, and that's where the highest temperature is and the higher pressure, and it will be then passed on back to the plate heat exchanger. Scroll compressors are fairly efficient, very efficient, they're reliable, and also the sound level is relatively low compared maybe to some other compressors. But there are other twin rotary compressors, also one which we have in our range, working similar, but the squirrel compressor is probably the most widely used compressor for residential areas. If you go larger in heat pumps for commercial applications, then we're talking about piston compressors and screw compressors. So it's a complete different ball game altogether. But these type of compressors are quite common for residential heat pumps and been around for many, many years. So then air source heat pumps are also inverter driven processes or compressors. And basically you need to think about it like a gas boiler. So gas boilers are modulating gas boilers, so they're modulating from a higher level down to a lower output level. With inverter driven compressors on air source heat pumps, this is more or less the same thing or similar thing. But it's more crucial for air source heat pumps because we have variable temperatures, especially with air source heat pumps. So they have to work between -10, -20 degree, all the way up to 20 degree or maybe warmer. So it's a big temperature difference they have to work with. And the warmer it gets outside, then potentially with a fixed speed compressor, the output of the heat pump will gradually increase. But we don't need that energy. As we know with heat pumps, like with gas boilers, you're sizing the unit to the coldest day in the winter through the statistics for the UK markets, average maybe -3 degree outside temperature. That's how we are sizing our heat generators too. And that also means that for air source heat pumps, we're sizing it to it at that point. The variable inverter driven compressor also has another advantage. They are reducing the need for any buffer tanks in the properties because they're modulating. So that's another advantage there. And we also have to bear in mind that the compressors do have limited on-off start-stop cycles. So as a comparison, maybe a gas boiler is now up to 250,000 start-stop as a life cycle design criteria. Compressors are maybe about 50,000, 60,000 start-stop. So the inverter-driven compressor will improve this lifespan, but also buffer vessels have in the past, and we're still using fixed speed compressors for ground source heat pumps, for example, that we do need buffer tanks to make sure that the lifespan of the compressor is still 15, 20 years.
And you can just allay John's fears about the pumps then managing in temperatures below freezing, that they don't freeze up, or is the minimum?
No, they don't. Yeah. No, they don't freeze up. We come to that in a minute. There is, however, there's a defrost function built in, but that's not. That's the reason for this is because of other reasons. But I will come to that in a minute. Yeah. Okay. This is just another graphic display here about the importance of inverter-driven compressors. So again, I said the outside temperature is is a big variable on air source heat pumps. So we are expecting them to provide the right heat demand at the coldest outside temperature. That's our plan. And then if you look at the black line here, this is sort of the proportional graph here of the heat demand of buildings. So the heat demand of a building is proportionally to the outside temperature. So the colder it gets, the warmer, the colder it gets, the more energy is required for the building to keep it up to temperature. And then the warmer it gets, the lower the energy demand is, all the way up to 20 degrees. And the air source heat pump is actually following that trend. Hence also that we are using weather compensated controls. But this is important because otherwise, as I said before, if the heat pump would not have an inverter driven control, and you can see that some of our older machines with fixed speed control, the output will just increase the warmer the temperature is outside, and we don't need that energy. It's just not required. So therefore we are modulating the output of the heat pump to the demand of the building. So that's where that is. So evaporator. So now we're coming to the freezing of the heat pump. The evaporator is a very important part of the heat pump. As I said before, it is a large heat exchanger, maybe not very obvious to everybody how important that is, but you need to bear in mind that we are absorbing obviously low temperature, low grade energy from the outside air, and then it's been absorbed by the refrigerant which is going through the pipes within the fin tube heat exchanger, and we need to make that as effective as possible and also as quietly as possible. But of course, the air changes all the time. We have warm air, we have humid air with the water content in there. And of course, if you then passing the energy through the fin tube heat exchanger, you do get condensation on the fins. The water needs to be drained off very quickly, very fast, very effectively. Water left on the fins will mean it will isolate the heat exchanger or insulate the heat exchanger, it's probably a better word, and therefore the heat transfer rate will be reduced and therefore the efficiency will go down. So that's a very important design element of this. So of course, the colder it gets outside, the fin tube heat exchanger with the water droplets there will start to freeze. And that's a very important part, that the freezing process of the evaporator is happening with any air source heat pump. Some of them are worse, some others are better. Again, it really depends on how the evaporator has been designed. So this is just an image here. It demonstrates the freezing, the ice build up on the fins on the heat exchanger, and that needs to be dealt with. Every air source heat pump has got some form of functions and functionality how to deal with this. If we don't do anything with the ice buildup, then the heat exchanger will just block up. And again, you know, if you look at your freezer, you need to defrost the freezer every few months because you have ice buildup in the cabinets, and that's causing the energy bills to go up. The same actually happens with the evaporator and the ice buildup on the evaporator heat exchanger. So it's a normal process. There's nothing to be alarmed of, but I would do query and installations where this happens for several times or too often during the day. It does usually happens if you have very damp and humid cold air, especially in the autumn or in the winter, and there's this freezing, icing up of the heat exchanger do occur. So we need to defrost it. And that's the word defrost of the heat exchanger. That's what we use. And the defrost cycle is something which is built in. But because we're using energy for the defrost cycle, that's also part of the total efficiency which we're claiming on the database. So the defrost cycle starts usually at the outside temperature of less than 5 degrees, and we're measuring the effectiveness of the evaporator. And at a certain point, we are sensing that the heat exchanger is due for defrosting. And what we do is we are actually taking the warm energy from the heating system in the house and reversing the flow. So therefore the evaporator, which is frozen up, is becoming our condenser, and the condenser in the house is becoming our evaporator. So that means that we are warming up the refrigerant and passing it into the evaporator, and the warmer temperature will start melting the ice. The whole process takes maybe about a few minutes, up to maybe 9 minutes. And it's only effective if we have sufficient amount of water volume in the heating circuit. If the heating circuit water volume is relatively small, then we have not enough energy available to do the defrost cycle. And that's again part of the reasons why manufacturers do stipulate that a certain minimum amount of water volume in the heating system has to be present. That can be aided with a buffer vessel or any other means of increasing the water volume. If the water volume is not there, then the heat pump hasn't got enough energy to defrost the evaporator, and then we are working throughout the winter with a partially completely frozen up heat pump, and the efficiency will be down, and the customer complains that he pays too much of electricity and the house doesn't get really warm. So very important process. So how do we do it? We are normally recommending that the heating system has to have a minimum water volume of 50 liter. Now, please do not consider the water volume in your radiators or in your underfloor heating circuit. The reason is because radiators are fitted with TRVs, underfloor heating systems are fitted with actuator valves. These are isolating the circulation, certainly in certain conditions. So this is what we call not a freely available water volume. So we are usually recommending that that's the water volume only to be considered from the heat pump to the nearest valve, two-port valve, TRV or whatever, and just count the water volume in the pipework. That's also the reason why we do recommend larger diameters than normal, 28 millimeter, if you want to get up to 50 liter, or installing a small buffer vessel. So we have small buffer vessels available, and they're up to 46 liter. So that would be meeting the minimum requirement. But that's a very important aspect, and that's the reason why most manufacturers do recommend a certain amount of water volume in your heating system. Very important. Okay, then we have the condenser. That's just a normal plate heat exchanger. Again, the larger the plate heat exchanger is, the more effective it's able to transfer the temperature from the refrigerant circuit to the heating circuit. And we are mostly running temperatures up to 65 degrees with heat pumps. If you make the plate heat exchanger very small, then obviously the effectiveness of the plate heat exchanger is not there, and you may be only getting maybe about 50-degree floor temperature out of it, or less than that. So it's very important that the plate heat exchanger is sized correctly. Good. So then another thing which always comes up is the difference between monobloc and split unit. I've used these two words here as well. Split units, as I said before, are usually machines which have got an outdoor unit and have an indoor unit, but they're connected with the refrigerant pipes. And these refrigerant pipes have to be installed and connected to the indoor unit by an F-gas registered person. So the advantage of having this type of system available is that obviously the refrigerant pipes are only 10 millimeter in diameter. So we have a small penetration through the wall fabric. And that helps architects as well, because they don't like it, making the house very efficient and having a large breakthrough through the bricks to get the pipes in from the outside to the inside. But the disadvantage is obviously you need to be F-gas registered, and also there's an annual inspection required to check the refrigerant leakages, etc. So monobloc units, we have just the outside unit there, and we're connecting then the outside unit with flow return pipes into the building. Some manufacturers, like Viessmann as well, we are offering an indoor unit for that, but that indoor unit will only house a circulating pump, expansion vessel, controller, etc., to make it all a bit neater. Some other manufacturers are not bothering with that. They just have the outdoor unit there, and then you fitting your 3-port valve and expansion vessel somewhere it's in the heating system. But this is the main difference. So here we have the whole refrigerant circuit included in the outside unit, and then you're just connecting the flow return to your building, while with the split unit, the refrigerant circuit is actually connected between the outside unit and the indoor unit, which has got the condenser fitted in there. So that's a key difference between these two technologies. Coming to the efficiency, another important thing, been widely talked about it, and it's on our hearts to make sure that we all understand why the efficiency with heat pumps is so important. So first of all, the efficiency on heat pumps is called COP, the coefficient of performance. So the coefficient of performance is determined during the manufacturing testing process. So every manufacturer, we have to test the machines to various standards and the test conditions. So we're testing it with air source heat pumps, we're testing it at various air temperatures and demand temperatures as well. And then we're getting a COP. So the best example here is that we have, for example, a heating output of 4 kilowatt from the heat pump, and we are putting 1 kilowatt of power into it. That gives us a COP of 4. The difference between 4 kilowatt and 1 kilowatt is coming from the ambient air or from the ground, so 3 kilowatt here from the environment. But these information are provided by manufacturers, and they're coming from laboratory testing. So they are on the spot, steady state performance data at various conditions. So with air source heat pumps, when you look at our technical data sheets, you will find quite a lot of technical data for -7 to -2, +2, +7, +12 degree at 35, 45, 55 flow temperatures. For all these conditions, we do have a COP data available, very important. The government in the UK, MCS, is calculating then a seasonal performance or a seasonal performance factor or an SCOP. We, in our controls of heat pumps, we also measuring the SPF for customers. This is a good indication to see how effective the heat pump is actually operating. So the longer the heat pump is running in an end user's house, we do measure the electricity requirements and the usage and how much energy the heat pump has been put into the heating system. And then we are calculating an SPF factor. Very useful information. And then settings can be changed to make the system more effective or maybe highlight some problems as well. But that's the main difference. So COP is the manufacturer's information on the spot, similar to gas boilers, temperatures, a rating of 80, 60 and 50, 30. These are also manufacturer's information from testing data, and the same as with the COP. So why is that so important, the coefficient of performance? Now, we do understand that gas boilers efficiency between condensing and non-condensing is maybe only 15%, 15%. So but with heat pumps, it's slightly different. We have here, apologies, we have here two scenarios here. So we have the temperature differential here, delta T, between the source temperature, which is our air temperature. So in this case, it's 0 degree, and flow temperature of 25 degree for underfloor heating. So this is the reason delta T of 25.A. Then we are running the heat pump with a higher temperature, maybe for radiators, maybe at 50 degree flow temperature. So this is our point B. So you can see that the efficiency drops from 6 COP of 6 or 600% down to 3.3. So this is a drop of 270% or 2.7. This is a significant efficiency drop if you run it at 2 different temperatures. So again, with gas boilers, we're only seeing a efficiency drop of 15%. So this is something which we have to be very mindful of when designing an air source heat pump in heating systems. So continuously running a heat pump at constantly of 50 degree flow temperature or higher will result in a very poor efficiency, and customers will pay for this with electricity bills which are going through the roof. And usual comment is also that the heat pump costs them more to run than their old-fashioned gas boiler. So that's something which we have to be very much mindful of. So rule of thumb, the lower you can run the heat pump on degree temperatures, then we're improving the efficiency by 2.5%. And also the source temperature. So you can see also the warmer it gets, then we're also improving the efficiency by 2.7%. So that's very important. We need to make sure that this is happening, and that explains also why we're all trying to make sure that the system has been upgraded sufficiently ideally with underfloor heating systems or special low temperature radiators.
So Christian, just conscious of time, we've got about 10 minutes left. I think that's probably answered we've got a couple of questions about different locations and types of homes to, retrofit and also install these heat pumps. Maybe we could tick a couple of them off, and then you can come back and give us a few kind of key messages and things that you haven't covered to take away. Is that good?
Say again. So I missed that. Sorry.
Yeah, we've got a few questions from the audience about different places or different types of houses to retrofit. So maybe we can take a couple of questions now, and then you've got some time at the end to make your
yeah.
So I think that probably covered one off from Jamie about he lives in rural Ireland. He's asked by lots of customers about replacing this old boilers with a heat pump, but worried about the lower temperatures. So it really comes down to this calculation in efficiency as to whether that it makes sense commercially. Is that fair? Do you have any kind of experience?
Yes, so absolutely. So with any application, so I'm naturally old buildings, and this is where the government is also fully aware of this situation. Oil boiler applications, oil boilers in rural areas tend to be older properties, and they are running at higher temperature. So replacing them with the heat pump is a challenge. It's a challenge, from the heat output point of view, which I'll come in a minute to this, but also is a challenge to provide an efficient heat pump. So it's not that the heat pump may not be able to cope with this. It's just we can run heat pumps at 60 degrees. But we have to be mindful of the fact that then the efficiency will be less favorable. Yeah.
So that probably also covers Colin's questions about old granite built or lath and plaster homes, considering retrofitting again.
Yes, so
that's fine. Yeah.
Yeah, no, I will come in a minute. I will have a quick introduction about sizing heat pumps, and that's exactly covering those points as well.
Great. And then one more, actually a couple more. One is seawater corrosion for people who live by the coast in Jersey. So can outdoor units pull in that air that has sea salt content?
Yes.
That's
yes,
okay.
you need to check with manufacturers. Some manufacturers do provide a minimum distance to the coast, so 1 mile or 1 kilometer distance to the coast is the minimum distance they have to keep. Some other manufacturers are quite flexible, and it doesn't really matter. I mean, as I said, the corrosion aspect, very important from the evaporator point of view. Is very important, and it's a good question, absolutely. But every manufacturer's got some other preferences and guidelines, and the models we use are suitable for coastal installation. Yes. Okay,
great. And then there's a couple of things about sort of training, and also for the Viessmann do you have a Viessmann helpline to call? If you need help designing the heating system,
yes,
provide all that information. That's great. And how Endra had a sort of suggestion. He was worried about going through expensive training. Can you produce pre-gas pipes so an installer doesn't have to go through that, or provide in-house training? What's your recommendation around that?
Yeah, I mean, we as a manufacturer, we are trying to make the installation of the heat pump as easy as possible. So from the heating engineer's point of view, that's an easy thing to do. As I said, the aspects here are obviously the recognition and the planning aspect there is very important. We do help customers with that as well. So if they're not sure whether the heat pump is suitable for this property or not, please contact us. It's not a problem. The installation is then mostly is just, I would say plumbing work, normal heating pipes. There's nothing major about it. We provide also hydraulic schematics. Yes.
Okay, great. Yeah. Cool. So you got sort of 5 minutes. I will just say to everyone, do keep sending your questions in. We will collate them, and even if we don't get to them in this hour, we'll do our best to try and put some answers.
Yeah. No, I'm trying to run through the other bits. Yeah, that's fine.
Okay.
Ben, is it possible to extend this by 10 minutes, or are you
Yep. we can extend by yeah, for sure, by a few minutes.
Yeah,
obviously
well,
conscious
that would be good.
people
Yeah,
may
it's got
have to
a
drop
few
off.
things there. I think the next slides, Ben, will explain the some of the questions as well. Yeah. Okay. So this chart here is showing you, it's an extract from our technical chart. So we are offering charts showing you the efficiency performance at different operating temperatures. So very useful if you want to have a look at it at various outside temperatures, what the efficiency is of the machine. So radiator sizing. So again, part of the questions came in is about can I use a heat pump for a normal property, which is usually radiators, don't have enough floor heating. So this is just an outline. You all know about this one, but most radiator manufacturers now offering the output of the radiator at different temperature differentials. So when it says delta T 50, it means that the output at a floor temperature of 70 and room temperature of 20. In this case, example here is one kilowatt of output of that radiator. If you want to run this same radiator with low temperatures, so 50 degrees, as I said, with the heat pump, then the output will drop to 500 watts. So that's nearly 50% immediately just by lowering the temperature by nearly 30%. So that's something which we have to be mindful of. Luckily, old radiators tend to be maybe a P1 or K1 radiator. So there is some mileage there to upgrade to a double convector radiator without really making the radiator any longer. Right? For example, if it's a K1, it's got 500 watts and you can doubling it up. So that's something which you know all about it, but it's just important to understand that this information is available, and then you could easily upgrade the radiators to make the heat pump operation more or less effective. So this is just, again, people come in and asking, well, how do I size heat pumps very quickly for clients? How do I see very quickly what heat pump, or is a heat pump suitable for this job? So this is just giving you 3 methodology I'm using predominantly to advise people. So first of all is you need to be very important is that you only consider the space heating requirements of properties for heat pumps. With gas boilers, people have added in the hot water performance, and that's maybe sometimes the reason why we're finding a 35 kilowatt heat only boiler in a new build property. For heat pumps, only space heating outputs being considered, not the hot water side of it. Then I give you 3 options here how to very quickly determine a heat output requirement with heat pumps. So first of all is the specific heat demand. Come to that. It's a very quick estimation. You can use customers' energy bills, and then the more complex route is the MCS heat pump sizing tool, which we can offer as well, and we help you with that. That's a more complex way of going to room by room situation, and then you select the heat pump from the data sheet. So starting off with the estimating the heat pump for property, the specific heat demand is expressed in watts per square meter of heated floor space, and you can use a table like here for different properties. And if it's an old property, you can see we have maybe 135, 150 watts per square meter heating demand, and the more modern or newer the property is, then the heat demand per square meter will reduce accordingly. Now, of course, these are just average figures. The state of the property in terms of, has the customer updated with double glazing windows, or so many super duper loft insulation in there, or wall insulation, etc. That is just giving you a quick indication. When you come to customers' properties, you look at the age of the property, you're doing a quick estimation in here, and say, well, okay, that building 100 square meter, I need about 11 kilowatt of a heat demand for the property. So that's how you use it. So you're picking up the specific heat demand for the age of the property, and then multiply that with the floor space area, and then gives you a good rule of thumb indications. So as I said, or rural areas using an oil boiler tend to be quite high, 150 square meter, then you're ending up here with about 19, 20 kilowatt. And then you see already that a heat pump replacement is not effective. The heat demand of the property is far too big. Yeah, so 100 square meter up to this one, it's maybe doable. But any bigger properties of that type, then you're struggling already finding the right heat pump powered with single phase power supply. So this is just a very quick rule of thumb guide you could use. The next one is the using customers' energy bills. So that's usually what I'm asking them to do, because it covers the behavior of the homeowner. So because some of them are maybe working constantly from home, which we all do now mostly, some are full-time workers and they have got the heating on maybe twice in a day. But the gas consumption on the energy bills can be used as follows. So you have, let's say, 15,000 kilowatt hours, and you look at the efficiency, or you ask how old the old boiler is. If it's a very old one, pre-2000, 2005, are using a efficiency of around 75%. If it's a modern gas condensing boiler fitted, then we can use 88%. So then you're multiplying that, you're getting a heat demand of 11,000 kilowatt hours. Then, as I said, you don't need hot water. I'm usually deducting then about 1.7 kilowatt hours per person per day. So, you know, roughly was it 2 people living in the property or 4? In this case, there's only 2. So I'm taking 1,250 kilowatt hours off, and I'm being left with 10,000 kilowatt hours, which is the heat demand over the year. Finding out what my heat load requirement is, I'm dividing this figure by 2,000 and gives me 5 kilowatt. So that's sort of the very rule of thumb. That's the calculation I use all the time. And even with it's commercial, it works all the time. It works very, very, very good, and gives you a very quick upgrade of or update on the suitability of using a heat pump. Okay. And then the more complex models are obviously the MCS sizing tool, for example, or any other heat loss calculations. You may use already some different ways around. You have to do then a room-to-room analysis. You have to, the MCS is basically asking what type of room it is, and then it defaults then the temperature, if you select the living room or bedroom or etc. Then you're putting the size of the room in there, and then also you're defining the age of the building, and then sort of puts defaults U value in there, and it gives you some good indications there. And then in the end, it kicks out a heat loss demand of 6 kilowatt here and 18,000 kilowatt hours energy demand for the year. So there are different ways of doing it. This is obviously more accurate by room. The others are just very quick guidelines there. Okay. Good. So then when it comes to selecting the heat pump, then I would like to ask them to go to our technical documentations. We provide extensive data for different operating conditions. So you decided you want to run the heating system at 45-degree floor temperature. Your outside temperature is about -3 degrees. Then this is the output of the heat pump, 5.4 kilowatt. That's your selection for this particular model, and then you're good to go with a very quick offer for the client before he makes a decision. Obviously, when the final decision is due, just double check the heat demand again, just to make sure that nothing has been forgotten. But that's sort of a very quick way of determining the feasibility of selecting a heat pump or not. Okay, so that's a quick update on that one. So then the final technical aspect there with air source heat pumps is obviously the sound level. Again, be very careful with the sound information a manufacturer's providing. They usually provide you with sound information. It's called noise level, and then give you a number. Usually the number is around very little, 40, 45 dBA, etc. But you still don't know, are they talking about sound pressure level or sound power level? Very, very important differences. And normally, as a manufacturer, we have to quote sound power level in our technical data. This is like the cause. This is what the heat pump actually do, but it's not audible. From the sound power level, we can then calculate the audible sound pressure level. So comparing it against the same effect with boilers or radiators early on, the electrical power or the heat power from the radiator is 1 kilowatt, which is our cause. And then with the radiator, that's our temperature effect. That's what we feel in the room. The same as with the sound pressure level with heat pumps. So sound pressure level and sound power level are different things. Unfortunately, they're using the same units, which causes that confusion. But this is something which you need to ensure that's very important and covered. So again, sound power levels, heat pump 65 and is standard 60 dB. Some models from Viessmann actually going down to 58, which is quite quiet. But again, what's important about air source heat pumps in the position? Now we have different location aspects with heat pumps. We're calling a freestanding wall-mounted installation and within corners. Now, freestanding, you have experience that yourself with playing children in the field, probably a football field as well. They can't hear you, you don't hear them. And this is because the noise levels are dispersing in all directions. Coming the children's closer to the house or maybe even in corners, between buildings, all of a sudden they're becoming really, really noisy and loud. The same happens with heat pumps as well. The closer they're to a brick building, concrete wall or building or between buildings, the appearance of noise of heat pumps are much noisier, and that needs to be considered. And therefore we are offering them different K values, which is a standard value. The MCS uses the same. And you can see that the K value increases significantly if the heat pump is located between buildings. So that's something which needs to be considered. And the quieter the heat pump is, the better, obviously, it is to be in positions like this. How can you suppress noise levels? Not with concrete walls. You can suppress noises with vegetation, hedges, plants, etc. Obviously more to the side, but concrete walls or brick walls do enhance the noise level, so that's not very good. Vegetation, soft fabrics are better to suppress the noise level. So that's very important to understand where the heat pump is being located. Using this classic example here from a normal street with different houses in here, which are the square boxes here, and you can see we have one fitted here. And with a noise power level of 65, the noises can be heard to the neighboring buildings, etc. And then potentially there might be an issue there with customers or neighbors complaining. So that needs to be considered. There are some building regulations which do quote about 40 dBA at the neighbor's boundaries needs to be met, or 39. So that's something which needs to be considered in the planning stage. If you use a quieter heat pump, you can see that the noise levels are obviously not spreading out so far, and even the neighbor won't hear the noise levels as maybe with some other models. So that's the reason why it's so important to make sure that the right size and the right heat pumps are being considered, and also the position has been considered as being feasible and not complaining. Good. So quickly, finally, some hydraulic schematics, very simple. You probably know this. I mean, this is just our current heat pumps, for example, here, the 200A, for example. We have a normal heating circuit to the hot water cylinder, which is a separate hot water cylinder. And then we have, we have a direct pipe to the heating circuit, ideally then on a floor heating circuit, with no further interruptions. To ensure the minimum water volume, as I've said earlier on, we have to perhaps fit a small buffer store to make sure that we have 50 liters of water volume in there. So, and a bypass. So we cannot consider the water volume in the underfloor heating circuit. So the water volume up to the actuators are what counts. And therefore we need to make some preparations to make sure that that is happening. And as I said before, the water volume is important for the defrost cycle of the outdoor unit. And then we have a very space-saving compact model, which includes a 220-liter unvented cylinder. Again, same element there, directly heating into heating system. We have all the components built in. But the beauty with this one is that we're offering what we call a backpack buffer, so at 40 liter, which is mounted at the back of the unit. So that means that the footprint of that machine is about 800 by 600 millimeter and 2 meter tall. So you can actually put it into space-saving recesses in the property and don't need much space to put in property or plant rooms or garages, etc. So it's a very attractive proposition here.
Okay.
Okay.
I think Christian, we're going to have to just about wrap it up.
Yeah, no, I'm finished now. So that's just final bit here. Yeah. So
great. So guys, thank you so much, Christian. That was
any quick questions or so you want to get rid of or not?
Fantastic. I think with a lot of the questions, we've still got probably about 10 or 12 ones which we can take and send replies.
And you can send them the answers.
We'll also publish to make this recording kind of available for people to watch and go back on demand.
Yeah.
And if you want to as well, just say any kind of final few words, anything you want to people to specifically remember, but also we'll pass contact details on so that people can get in touch after this event. So guys, so thank you very much.
Yep.
Thanks very much for joining, and hopefully see you at some of the more webinars in the future, or perhaps in person. Brilliant. Thanks everyone.
Yeah, well, thank you very much to all. Yeah, thank you very much.
Great.
Yeah.
Thanks, Christian.
Okay.
Thanks everyone.
Bye bye.